Alright, we're talking about 5.1 and 5.2, which are polygon angle sum and exterior angles of polygons. Okay, so first things first is 5.1. Okay, remember that a polygon is just a multi-sided or many-sided closed figure with straight sides. There are no curves. Okay, they are all straight sides, and it's closed. There's no openings. Okay, and poly just means many, so it's a many-sided figure. You will sometimes see it called an in-gon, okay, where in represents the number of sides in the polygon. Okay, so you could call this a 3-gon, a 4-gon, or a 5-gon. Okay, but the lower numbered polygons have specific names. For instance, we know this is a triangle. Okay, this is a quadrilateral. 5-sided is a pentagon. Okay, you should learn them or know them up to 10-sided at least. Okay, and then you could start calling them in-gons. Okay, we know when we talk about angles on the inside of a polygon, we've worked a lot with triangles, and we know that the 3 angles of a triangle should add to 180 degrees. Okay, well, what's going to happen as your polygon increases in size, or in number of sides, I should say? Okay, each time you're going to add 180 degrees for each side. So a 4-sided figure then would total 360 degrees. Okay, and then if we continue this pattern, okay, a 5-sided figure, or a pentagon, is going to have 540 degrees. Okay, this does not mean necessarily that these angles are all equal. Okay, they're not each 540. Okay, they total 540. Okay, so if you're given 4 angles, you can add them together and subtract from 540 to get the 5th. Just like we've done a lot of practice with triangles. When we knew 2 angles, we added them together and subtracted from 180 to get the missing 3rd angle. You can do that with any polygon, okay, if you know the total that you're supposed to subtract from. Okay, so here the quadrilateral sum conjecture just states that the sum of the measures of the 4 angles of any quadrilateral is 360 degrees. Okay, same thing for a pentagon. The sum of the measures of the 5 angles of any pentagon is 540 degrees. Okay, now we're going to carry this over, this pattern, to fill out this chart. Go ahead and put in 360 and 540, and if we continue to add 180, that's going to give us 720. Okay, and then if we add another 180, that's going to give us 900, and if we add another 180, that's going to give us 1080 or 1080. Okay, so what's happening here, we know the pattern is plus 180 each time. Plus 180. Plus 180. Okay, but if you get to a very high number, that's going to take you a while to get there if you just have to start with 180 and add for each number of sides greater than 3. Okay, so we're going to write an equation. Okay, and we did this several weeks ago, looking at tables and coming up with the function or the equation. Okay, so the change, remember, that's what we multiply by. Okay, so the change is 180. So it's going to be 180 times something. Okay, so 180 times something. Okay, so we're going to come back over here and figure out what that times is. Okay, so this is our first figure. It's 3-sided. Okay, so it's not 3 times 180, because that doesn't give us 180. If you look, what times 180 is going to give us 180? And it's just 1. Okay, well, what times 180 is going to give us 360? It's just 2. What times 180 will give us 540? 3. And notice we're just increasing here by 1 each time. Okay, so if you look at the comparison from the number of sides, or your in, to what you're actually multiplying by, these are 2 less. Okay, 1 is 2 less than 3. 2 is 2 less than 4. So you're subtracting or taking away 2 from the number of sides. And we said the number of sides is represented by n. So this would be n minus 2. So you're multiplying n minus 2 times 180 to find the total, okay, the sum of the interior angles of a polygon. Okay, we already mentioned that they can be called n-gons. Okay, so this conjecture or rule states that the sum of the measures of the interior angles of an n-gon is n minus 2 times 180. That's your formula. It doesn't matter if you write the 180 in front or behind as long as the n minus 2 is in parentheses so that you know to do that subtraction first. I'm just going to help you understand this a little bit better with this diagram, okay, because you are very comfortable with triangles by now. So if you look at your polygons as triangles, okay, this may help you see why we're multiplying by n minus 2. So here, if I draw this diagonal, I've split this quadrilateral into 2 triangles. Okay, let's see how many triangles this would split into. So if I drew a diagonal here, here's 1, but this still isn't a triangle. I got to draw 1 more. Now these are all triangles, so I have 3 triangles. Okay, if I do the same thing here, there's 1 triangle, there's a second, third, and fourth. Okay, so when you break your polygons into triangles, quadrilateral breaks into 2, and we know that a triangle is 180, so you have 2 times 180 is 360 degrees. Okay, this is 3 triangles, each of which is 180 degrees. So you have 3 times 180, which is that 540. Okay, this is broken into 4 triangles. Okay, this one is a hexagon, it's 6-sided. Okay, so 4 times 180 is 720. Okay, and you could do this with any polygon, break it down into triangles to help you see what you're supposed to multiply 180 by. Okay, so that's where that n minus 2 is coming from. It's how many triangles the shape breaks down into. 5.2 is now going to talk about exterior angles of polygons. Okay, that formula you just wrote down, n minus 2 times 180, is only for interior angles, inside the shape. Okay, so exterior angles, if you look here, it's if you extended the side of your polygon, okay, you create these angles. They're on the outside, they're exterior. Okay, we're going to talk about what those are going to add up to. So here I've drawn a hexagon for you, and just to save some time, I've already used a protractor and measured these angles. Okay, if you want to practice this some more, you can draw any polygon, any size, and use a protractor to go and measure those interior angles. Okay, so if this is what we have, we can find exterior angles using our linear pair rule, because if you see at each of these where this side is extended, okay, you have these 2 angles, okay, they're forming a straight line, which hopefully by now you're comfortable and it comes to you quickly that this is 180 degrees. So this line is 180 degrees, and I've used 97 degrees. Okay, so 180 minus 97 to get what's left, and that's 83. So we have 83 degrees left for the exterior angle. Okay, this is going to work all the way around. These are all linear pairs. This is a linear pair, 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 and pair. So you're going to go around your polygon and subtract pardon the bell, but you're going to go around your polygon and subtract each of the interior angles from 180 to get your exterior. Okay, so this leaves us with 60 degrees here. Okay, we do the same thing all the way around. Okay, and so here we get 32. Okay, 180 minus 103 is 77. 180 minus 114 is 66. And 180 minus 138 is 42. So here you have your exterior angles now. Okay, these are the exterior, outside. If we go and add these up, add up all the exterior angles of your polygon, and again, mine's a hexagon, but you could do this with any polygon. No matter how many sides your polygon has, when you add up the exterior angles, it's always going to be the same total, and when we add this up, it totals 360 degrees. Okay? So again, if you used a different shape, you should have gotten 360 as well. So no matter what they are, in this one, this is a pentagon, if we went and measured these angles and added them, it would also be 360 degrees. So the conjecture that you need to write down states that the exterior angles of any polygon, okay, is going to total 360 degrees. So the sum of the measures of the exterior, that's the important word, is 360. So you don't have to remember a formula like for interior, just this singular number, 360 for all shapes. Okay, now if we're dealing with regular polygons, regular in geometry means all angles equal, all sides equal, or congruent. Okay, so in this one, these are all marked congruent in all of these examples. Let's look at this middle one first. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8. So this is an octagon. Okay, so we have 8 angles, and we want to figure out what those are. Well, we could do 8 minus 2 times 180 and figure out the total degrees and then divide it evenly between the 8. Or you could use your exterior angles. That might be a little quicker because we know the exterior angles add up to 360, and I know there's 8 of them and they're all equal. So all I have to do is take 360 divided by 8, and I know that each of the exterior angles is 45 degrees all the way around. All of these would be 45. Okay, and then I can use my linear pair rule. These interior and exterior angles together total 180. So then you would just do 180 minus 45 to get what's left for your interior angle, and that's 135 in this case. So each of these, since they're all congruent, would be 135. Okay, you could try that for this 11-sided figure or this 4-sided figure as well. Okay, now the rule that you're going to write here says that you can find the measure of each interior angle of an equiangular n-gon by using either of these formulas. Okay, so that's either of the ways I just explained. So the first one is by taking n minus 2 times 180, getting your total, okay, and then just dividing by n, how many sides there are. Okay, or the second one is by using your exterior angles. Okay, so you do 360 divided by how many angles there are, and you subtract that from 180. Okay, so either of those rules or formulas can be used to find the interior angles of a polygon. Okay, so hopefully that's pretty clear to you now. You've done some practice on 5.1, and when you come to class Tuesday, we're going to practice some of 5.2.